Welcome to Oddly Real. I'm Nem Stefanovic. I wanted to dedicate an episode to a truly extraordinary substance, water. Water is essential to life on Earth and quite possibly everywhere. It's very likely that life began in water. Biological cells contain between 70 and 95% water. We all know how critical water is to our daily lives and how valuable it is as a resource. We need to drink water daily. We use water to clean ourselves and to carry away dirt and waste through our plumbing. We use water to irrigate our lands, to grow our food. Additionally, water has been a major focus in geopolitics since many countries in the world have limited access to natural fresh water. This can result in conflict and war, but it also results in innovation such as water desalination techniques. Regardless of this critical role that water plays in our everyday lives, water is also a substance with some truly remarkable properties. In this episode, we will explore those properties of water to demonstrate how odd and astonishing water is. Let's start by talking about the composition of water. It's composed of 2 atoms of hydrogen and 1 atom of oxygen. Hydrogen is the most common element in the universe and accounts for 75% of the total mass of all visible matter. Moreover, 90% of all atoms in the universe are hydrogen atoms. It might surprise you to know that oxygen is the 3rd most common element in the universe, constituting about 1% of the mass of visible matter. The water molecule has 2 covalent bonds between the hydrogen atoms and the oxygen atom, such that the stronger electronegativity of the oxygen pulls the shared electrons more towards itself and away from the hydrogen atoms. This unequal electron distribution makes the molecule polar, where the oxygen atom of the molecule has a partial negative charge and the hydrogen atoms have partial positive charges. The polar nature of water molecules results in atypical properties for the substance as a whole. Positive hydrogen atoms in one molecule are attracted to the negative oxygen atoms of a neighboring molecule. These attractions are called hydrogen bonds. Each molecule can hydrogen bond to at most 4 other water molecules. These bonds are far weaker than the covalent bonds in the molecule, about 1/20th the strength. But they form, break, and reform readily between molecules, making the water molecules very sticky. Each hydrogen bond exists for only a few trillionths of a second, but at any instant of time, a very large portion of the water molecules are bonded to their neighbors. In fact, 15% of the molecules of water in the human body are bonded to 4 neighboring molecules at any given time. The stickiness of water is what allows water to be transported up from plant roots to the rest of the plant. For example, if water evaporates from a leaf, the water molecule that is leaving tugs at the molecules behind it. This allows evaporating molecules to get replaced by water molecules further down from the vessels and the veins of the leaf. The water molecules are also attracted to the surfaces of the vessels themselves. The upward pull is transmitted through the vessels all the way down to the roots. The ultimate result is that water can flow up through the plant against the pull of gravity. Hydrogen bonding also relates to water's surface tension, or the measure of difficulty to stretch or break the surface of the liquid. You can imagine that something wanting to enter water, let's say from air, would have to break through a water surface barrier. The water molecules at the surface are positioned in an ordered arrangement so that they are attracted to the molecules below the surface. Water has a greater surface tension than most other liquids. Water also acts as a temperature regulator. It has a high specific heat, which means that it can absorb or release a relatively large amount of heat for a small amount of change in its own temperature. This property lets water absorb heat from warmer air or release stored heat to air that is cooler. The high specific heat is again related to the hydrogen bonding. The small change in water temperature relative to added heat is due to the fact that much of the heat energy has to be used to break hydrogen bonds before the molecules can be freed up to move more quickly and increase the temperature. Conversely, when the temperature of water drops, the hydrogen bonds form quickly, releasing considerable heat. Thus, a large body of water like a lake or ocean can absorb and store a huge amount of heat from the sun during the day or in the summer, while only warming up a few degrees. At night or during the winters, as the water cools, the heat from the water can warm the cool air. In addition to regulating land and air temperatures, the specific heat of water also regulates ocean temperatures, making a stable environment for aquatic life. Moreover, water also has a high heat of vaporization, meaning that it requires a lot of heat to cause water to evaporate. This contributes to water's high boiling point at 100 degrees Celsius, which makes water much more plentiful in liquid form on Earth, which further helps to ensure temperature regulation to make conditions favorable to life. Another unusual property of water is that ice will float. Water is one of the few substances that is less dense as a solid than a liquid. This can also be attributed to hydrogen bonding. Most liquids will expand when they warm up and contract when they cool down. Water behaves the same way down until 4 degrees Celsius. At this point, the water molecules are not moving fast enough to avoid being restricted through hydrogen bonding. When water hits 0 degrees Celsius, the molecules will lock up into a crystalline lattice, ice. Each molecule bonds with at most 4 partners. Due to the structural arrangement of the molecules in this lattice, the molecules are kept somewhat further apart, resulting in ice becoming about 10% less dense than water. It turns out that the capacity for ice to float is another critical component to support life on Earth. If ice didn't float, then the ice that would form at the surface of lakes and oceans would sink. This process would continue, with water at the surface continuing to freeze and sink until the entire body of water was frozen solid. Additionally, when temperatures did rise, only a few shallow top layers of larger bodies of water, like ocean water, would have a chance to thaw. Instead, when ice forms, it creates an insulating layer at the top of bodies of water that serve to insulate the liquid water below. We've already discussed numerous examples of how incredible water is as a substance. But there's even more, so we'll give a few more examples. Water is the most versatile solvent that is known. Water can be mixed with a variety of solutes that will dissolve in the liquid. This is what we see when we mix water with salt. We can attribute this capability to the polarity of water molecules. The water molecules surround the ions of the salt atoms to separate them from the salt crystal and shield them from other ions. This also works with other polar substances like ammonia. Water is not able to dissolve nonpolar compounds. However, an enormous number of solutes are dissolved in biological fluids such as blood or the liquid in cells, which makes water ideal as a solvent for biological systems. The cell is like a little factory or laboratory in which it is constantly producing chemical compounds. This is possible because water acts as the medium to allow the chemical components to interact and react. Water also plays a major role in human energy production. When hydrogen and oxygen combine to form water, they release a significant amount of energy. In fact, it produces 3 times the amount of energy per unit mass of gasoline or diesel fuel. The difference being that hydrogen is a gas at normal atmospheric pressure, so it still has a low unit energy per unit of volume. For example, the energy density of hydrogen at atmospheric pressure is a quarter of the amount of natural gas. This process can also be reversed, whereby water is separated into its constituent components of hydrogen and oxygen by passing direct current electricity between 2 electrodes immersed in water. This process is called electrolysis, and it requires energy to separate the substances. The hydrogen and oxygen can be collected at each electrode respectively and can be combusted once again to release energy. A fuel cell is an interesting technology that provides a means for hydrogen and oxygen fuel to be converted into electricity at a higher efficiency than can be achieved by burning them in an engine. The fuel cell works by pumping in hydrogen and oxygen to generate DC electricity with a byproduct of water and some waste heat. There are no moving parts. In a hydrogen fuel cell, a catalyst separates hydrogen molecules into protons and electrons, which take different paths. The electrons go through an external circuit, creating a flow of electricity. The protons migrate through the electrolyte where they unite with oxygen and the electrons to produce water and heat. The power efficiency of these cells ranges from 40 to 60%. This is better than the efficiency from engines running on natural gas or hydrogen. Finally, water in the form of steam is still the preferred medium for transmitting power from a power plant reactor to turbines to produce electricity. Power plants vary in their power production source, whether coal, geothermal, nuclear, or other, but many of these will use this energy to boil water into steam to send to a turbine to produce electricity. Steam can hold much more potential energy than water in liquid form, and it is easier to extract the energy into a more useful form. The steam produced in power plants is under high pressure at high temperatures to hold more heat energy. There is actually much more that we can discuss about the extraordinary properties of water, but we'll leave it at that for now. I hope you found this episode interesting. Remember, oddly real, really interesting.